Hello and welcome to DataCast Solutions, Statistics and Data Mining 101 using KNIME. In the last chapter we looked at measures of central tendency. Now we're going to look at measures of variability. While we identified the center of the data set, now we want to talk about the ranges and the measures, the variation from that center, and the various ways we measure them. There are a number of different ways that statisticians use to identify the measures of variability, and they range in complexity. The most simple ones are range and interquartile range, and then they gather in complexity when we deal with variance and standard deviation. So we'll look at each one of these individually. The most simple of these, of course, is the range, which is simply equal to the minimum value of the data set and the maximum value of a data set. So in this case, the highest value is 9, the lowest value is 1, so the range is 8. When we look at the output of the KNIME statistics node and the statistics table itself, we can see the minimum and maximum values. They don't have a specific value computation for the range, but obviously that would be easy enough for you to add if you needed that as an actual computation by taking the maximum minus the min. For example, I could take the expression node and add a computation to say the range, and the range is going to be equal to the maximum minus the minimum. And if I evaluate the column of the first row, you see I come up with 44. I would actually like the output of that to be an integer. And now I've computed a range column, which I can drag over here, get it close to the min and max, or resort the columns so that I can see them together. All right. So there are some very easy pros and cons to the calculation of range. It's very easy to calculate. One expression, maximum minus minimum, retrieves a value of 8. The problem with range, however, is that it ignores the middle values, and the outliers are very easily distorted. Look at this new example now. Data set B, where I've got all values of 1 and one value of 9, which also leads you to believe the range is 8, but the outlier is what's really distorted that value. So the next slightly more complex layer is the interquartile range, IQR. And it's also a measure of availability by dividing the data set into quartiles, 4 quarters. They're divided a rank-ordered data set into 4 equal parts, with the dividers between those parts being Q1, Q2, and Q3 respectively. The computation actually begins with computing Q2, which is the median value of the entire data set. Then I can compute Q1 is the median value of all values below Q2 in that data set. And Q3 is the median value of all data above Q2 in that data set. And then finally, the interquartile range will be computed as Q3 minus Q1. Let's take a look at how KNIME does this. So first let's look on paper. I have a data set ordered 0 through 9. I'm going to start by computing Q2, which is going to be the median of the data set. And since this is an even number, it's going to be the median of 4 plus 5 divided by 2. So 4.5 is the value for Q2. That's the median of the data set. So with Q2 calculated as 4.5, let's look at how we calculate Q1, which is the median values of all that below Q2. Since we have 5 values, it's an odd number, it falls directly in the center, so the value of Q1, the median, is going to be 2. And now all the values above Q2 are the numbers that will fall into Q3, and the median value of that is going to be 7, again, since it's an odd number. This thus allows us now the interquartile range of Q3 minus Q1 is going to yield an interquartile range of 7 minus 2 equals 5. Now let's look at the exact same data set, but we replace the 9 with a 999, an outlier, and see how the value is different. The value of Q2 still remains the same. And when we compute the value of Q1, it is also still the value, all those below Q2, which is also 2. And the median of those above the Q2 is still going to be 7. So just as it was before. Now we're able to compute the interquartile range as either Q3 minus 1, which is still going to yield a value of 7 minus 2, or 5. So the benefit of this method is that the outlier has not distorted the actual range calculation. Let's go ahead and take a look at how to do this and how to view and sample the IRQs in 9. I'm going to start with the my data set as 0 through 9, just as we've seen in the previous example. And then I'm going to execute the box plot node, and I'll go ahead and execute that and open the views for it. And there's my box plot. So I've now got values running from 0 through 9, and I can see the quartiles now. There's the median, which is IRQ2, and there's Q3, which is set at 7, just as we expected, and there is Q2, which is set at 2. And then the IRQ range, of course, then would be 7 minus 2, which is 5. I can also right-click and look at the output of this, and I can see the robust statistics for it. And here you can see, so there's my minimum smallest quartile 2, right there at 2, quartile 1, quartile 2, and quartile 3, and the largest maximum. So that's the main statistics that I would need. Now let's go ahead and go back here again, and let's change this to 999. And when I execute with this much of an extreme, now the scale has changed. So even though the box plot hasn't been altered, you see if I hover my mouse here, I can still see it's where I expected it to be. If I bring the mouse back over there, it's still sitting at 7 and 2 and 4.5. This extreme measure up here, the 999, but this is what's causing my problem. So with mouse selection mode, I can't get in here to actually see the data. But if you want to go into zooming and moving, you can actually go in here to see the box plot. But that's why it's so squished up like that. However, when I view the robust statistics, again, I can see now my maximum and then the largest and smallest are now properly identified. The next measure is actually called the variance, and it's more complex to compute, although of course just as easily in 9. But it provides the statistical average of the amount of dispersion for the distribution of a specific piece of data. It's not often used by itself, but it instead is actually part of the computation of standard deviation, which is what we'll get to next. To calculate the variance, what we are doing is looking at each individual observation and subtracting the mean from it, summing that up and squaring that value, and then dividing it by the number of observations itself. So whether we're doing a population or a sample is a minor difference, and that's n versus n minus 1. Otherwise, the calculation is essentially the same. And this altogether computes the variance of a data set for an individual observation set. The numerator portion of each part of that equation includes a sum of each individual observation and its distance from the mean squared. And this is called the deviation sum of the squares. So let's use a simple example to show how this is calculated. I've got the values of 0, 1, 5, and 6. And my formula, we assume that this is a population. So it's going to be the sum of the squares from the distance divided by n, which is going to be 4. So the number of entries I have, n equals 4. The mean is going to be equal to sum of x divided by n. And then the deviation of the sum of the squares is going to be x minus m squared. So if I plug all this into the formula, you see how I compute the mean as 0 plus 1 plus 5 plus 6 divided by 4. So the mean is 3, 12 divided by 4. The deviation of the sum of the squares is for each individual observation then. 9 plus 0 minus 3 squared, 1 minus 3 squared, 5 minus 3 squared, 6 minus 3 squared. That comes up with a sum, deviation of the sum of the squares to be 26. And then the variance is going to be 26 divided by the number of entries, 4. So the variance is going to be equal to 6.5. So here within 9, I've gone ahead and created the table again, 0, 1, 5, 6, just as we had seen before. And when I execute the statistics against that table, now you'll notice the mean is still 3, but the variance, I came up with a different answer with 9, 8.667. Well, how did we do that? Well, if we went back again and we said the grand total of our values was 26, so I'm going to call up the calculator, and let's remind ourselves 26, but instead of 4 observations, if I divided it by 3 observations, I get 8.667, which is again the value that 9 provided. Recall, so what's happening here is 9 is assuming that this is a sample, not a population that's being, so instead of dividing it by n, they divided it by n minus 1. Just as the formula 2 slides previously had shown us. So keep that into account when you realize that as far as 9's concerned, it's working with sample data. The weakness in the variance calculation is that by squaring the differences from the mean, we're distorting the understanding of the data itself. And as I give you here in the example, what if we looked at employee age? Well, if you square the age, what does that mean? I was 15 and now you take me 15 times 15. How does that help you? It's distorting your difference from the. So that's why the variance is very rarely used within a calculation, and instead it's a step to another calculation, the standard deviation. The standard deviation is a measurement of how concentrated the data is around the mean. Are most of the records and values observations close to the mean, or are they distributed? The larger the standard deviation, the more distributed the data is. So it's computed simply as the square root of the variation value. So again, you can see using our old friend, the population and sample, we've taken the exact same calculation, except we've taken the square root of the answer, and that's what computes standard deviation. So in this simple example here, assume that I have a variance of 100, then my standard deviation is going to be the square root of 100, which is 10. If, on the other hand, my standard deviation was 4, and you know therefore 4 was the answer of the square root, then 4 squared would be 16. So if the standard deviation is 4, that means the variance was 16. Since the standard deviation is a measurement of how clustered the data is around the mean, there are times when that's good and there are times when that's bad. If you're manufacturing a product, for example, you might say that I want my products to be as close to each other as possible. So the changes in diameter of a Pepsi can, for example, might be just microscopic, and the actual measurement of the diameter of the can versus the mean should be almost identical, very tight. But in real world situations where data is spread out, large standard deviations are expected and certainly normal in most cases. As I've mentioned before, outlier data easily affects the calculation, especially both in variance and standard deviation. So in my favorite working example, the highest paid running back on that football team, their salary is going to dramatically impact the average salary and the standard deviation, and the mean. All of that is affected by that outlier data. And of course with KNIME, again, looking at our simple standard example I've been working with here, if I look at the statistics table being generated, standard deviation is just one of the standard fields that is generated. So I get to say, here's my mean is 3, the standard deviation is 3. All right, for a chapter summary, range, it's just the largest minus the smallest, easy to calculate. It ignores the middle, however, where the IRQ is a better solution one because it's not influenced by outliers. The variance is the average squared deviation from the mean, but since we're squaring that deviation, it proves to be a misleading value, so we create the standard deviation, which is the square root of the variance. That completes this chapter of the class. Feel free to move on to the next chapter.